Okay, good afternoon. Let's continue with our discussion of the introduction, which is circuit variables. And then we look at circuit elements if we can. Okay, so I believe we stopped here, circuit theory. Okay, problem solving. So the engineers, you'll be faced with new problems every single day of your career, right? Yeah, there's a standard approach that we take for performing analysis or basically to any kind of problem solving, right? For electric circuits, I typically like to say that first identify the problem, extract as much information as you can from the given problem statement. Okay. So extract as much information as you can from the given problem statement. Now, sometimes the information is not explicitly stated, meaning it's not always there in the problem statement. As an example, you might be given a circuit diagram. The circuit diagram might be consist of several different components. So the values may not be given in the problem statement. It may be given in the circuit diagram itself. Okay. It would be your job as an engineer to inspect that diagram and extract information from there. Second is oftentimes you will receive problems that will have graphs and charts. In graphs and charts, you will have some information in there like values, time, frequency. For example, we saw these, right? Now there's a ton of information in here. You will see this in 211 and 212, but this is a standard representation of a sinusoidal waveform. That tiny expression in there, 2 cos 2 pi t, gives me information about the value of that voltage or current, gives me information about frequency, also gives me information about the phase. Okay, so there's 3 quantities included in this expression. So again, if you have graphs or charts, information will be embedded in the graphs or charts also. Time in seconds, sometimes it might be frequency, depending on what kind of plot you're looking at. But anyway, the point is that as EE students, as engineering students, you first identify the problem statement, inspect the problem statement, extract as much information as you can from the given parameters. So you'd have the problem statement, you might have some circuit diagrams, you might have some graphs, some charts. Extract all the information that you can. Then, oftentimes, we also need to modify our circuit. Okay, circuits modified based on certain conditions, based on some time analysis. You might say, okay, analyze the circuit between 0 and 0.2 microseconds, and then analyze it again between 0.2 and 0.4 microseconds. There are cases where circuits change, right? Systems change. They are not constant all the time. So systems change. If you're analyzing for a particular period of time, a circuit could change. So redraw the diagram as many times as you need. Okay. For instance, if you have resistors in parallel, you might combine them into one single resistance. So then you would redraw the circuit diagram. I'm very fond of the statement, redraw the circuit diagrams until it starts to make sense. So as a student, that's how I learn. And that's also what I like to instruct students in doing. I have a circuit diagram. On first viewing, it may not make sense, but I'll go in there, I'll modify the components in a way, and then I'll try it 2 times, 3 times, 4 times, as many times as it needs. I keep redrawing it until it starts making sense. All right. Sometimes connections are not very obvious. Okay. So again, sketch take the circuit diagram, redraw it as many times as you need. And then you apply your analysis techniques. Depending on what the problem is asking, you can choose from a variety of analysis techniques, perform your calculations, determine the answers, determine values, and then you verify whether your answers are correct. Sometimes there are multiple pathways to determine the same value. And so if there are multiple pathways to determine the same value, then you use the second method, the third method to verify your answers. Also, you can verify your answers to see whether it fits the boundaries of the given system. Okay. So you verify whether the values are correct and whether they make sense. Recently, last quarter, I had I think one of the homework assignments that I was looking at, some particular student, I don't remember what it was, but it's an example on where you can do a very easy verification check. The circuit had a power supply of 15 volts, I believe, 15 or 16 volts. And the end answer was about 17 or 18 volts at a certain particular point in the circuit. Because the steps were correct, the method was correct, everything was correct. There was some minor error in the calculation. So, easy verification. If your power supply is 15 volts, no point in the circuit can be more than 15 volts. It's an easy verification, right? Make sense? Right. And so that's something that you should keep in mind. And even after so many years, sometimes I end up making that kind of mistake. Okay. I'd go through the solution, I'd go through the analysis, and I'd arrive at an answer, and I move on to the next step because I'm in a rush. And then later on, I come and take a look at it, and it's like, okay, this is more than 10 volts. It's not correct. So I'd go back and redo everything. All right. So that's an example. When I say make sense, that's just one kind of example, right? Total energy in a system is confined. If your power source is 10 volts or 2 amps or whatever it is, your result at any given point in the circuit cannot be more than that value. All right, typical electric circuit. I'm assuming students are familiar with the components from physics at all. Maybe, maybe not. I mean, we're going to look at all of these components individually, but I just want to understand. How many of you are familiar with all of the symbols in here? Okay, most of you are, so that's good. All right, so resistances are drawn with a zigzag jagged edge symbol, right? Resistances. Resistance is basically opposition to the flow of current, flow of electric current. And again, we'll take a look at this in chapter number 2. This is just to show you, what exactly is it that we're trying to do. So we have resistors, we have capacitors, these are energy storage devices, and then we have inductors. Symbols for all three is R, C, and L. Spiral coil actually notes that it's a wound conductor. Okay, spirally wound conductor. All three of these are referred to as passive elements. Yeah, they are passive elements. They're passive linear elements. So the analysis that we perform is linear circuit analysis. Okay, linear circuit analysis. So we don't look at capacitors and inductors until we get to 211. Okay, this is purely resistive circuit analysis. So all three are passive elements. And also linear elements, passive and linear. These two are also capable of energy storage. Okay. So the three major components in electric circuits are resistors, capacitors, and inductors. Resistors, capacitors, and inductors are all passive elements. They're all linear. The linearity refers to the relationship between the voltage and the current. So for all three components, if voltage increases, the current increases, and vice versa. If voltage decreases, current decreases, and vice versa. In addition, capacitors and inductors are energy storage devices. Okay, they can store energy and they can release it back into the circuit at a later point in time, depending on the various circuit conditions. But again, the focus of this course is not capacitors and inductors, it's resistive circuit analysis. So what exactly is circuit analysis? Well, simply stated, circuit analysis is the process of determining the values of unknown quantities in the circuit. The unknown quantities in the circuit are basically voltage, current, and power. Okay. So again, circuit analysis entails determination of the unknown quantities present in a circuit, which is basically voltage, current, and power. That's all circuit analysis is. Okay. Determination of unknown quantities. Yep. Voltage, current, and power. And we'll look at all of these techniques in chapter 2. We'll look at power in just a little bit. Yes. Sorry, what? Resistance? No. So question being asked is, well, yes and no. Question being asked is, are resistors unknown? Like part of circuit analysis? Do we need to determine the resistances? Sometimes yes. Sometimes yes. But as we go along in the course, we are trying to learn circuit analysis techniques. So when we learn circuit analysis techniques, most of the example problems are already solved, right? So students are provided with the circuit, they're provided with the component values, and then you apply circuit analysis techniques to determine the voltages and currents. But having said that, you could be given voltage and current and asked to find the resistance. That is a very valid problem. Okay. So some cases, yeah, you would need to calculate and determine the value of the resistors. So far, so good. So I'm assuming the physics prereq is done in winter, or you're taking it now? Are you taking it now? So show of hands. Have you heard of, are you familiar with Ohm's law? Okay, good. How about KVL? Kind of. KCL? Heard of. Even if you're not, we're going to practice all of that. We're going to practice until you get sick and tired of it. Okay. But you've at least heard of KVL, KCL, Ohm's law, right? These are the only three principles and laws you need to solve any circuit. Okay, this entire course, all circuit analysis techniques are based on these three. That's it. Ohm's law, KVL, and KCL. There's nothing more that we need. These are the only three that exist. Every other technique is derived from these three. Okay. Sometimes it's not possible to solve it directly. And so we come up with new techniques, to generate more equations. The more equations we have, the easier it is to determine the solution. But Ohm's law, KVL, and KCL, these are the only three fundamental laws that we need for the entire, entire circuit analysis. Okay, so since we talked about voltage and current, brief recap or brief explanation about voltage and current. Law of conservation of energy applies to all systems, right? Energy is neither created nor destroyed. It's only transferred from one form to another. So when we apply, let's say, apply an electric field, there are charges that are moving in a circuit, right? Charges are moving in a circuit. When charges move in a circuit, we can define the separation of charges as the difference in electric potential, and we refer to it as voltage. Okay. So if charges are separated while they're moving in a circuit, if they're separated and there's a difference in the electric potential between these charges, we define it as voltage. Mathematically, voltage V is dW over dQ. W is energy, Q is the charge. Okay. So it is the electric potential difference. The difference in electric potential between those 2 points. Okay. When charges move through the circuit, through any component, through conductors, resistors, through anything, we look at the rate of flow of charge and we define it as current. So current is the time rate of flow of charge. Simply stated, I is dq over dt, derivative of the charge with respect to time. Okay, I is dq over dt, rate of flow of charge. Let's take a pause. Let me know if you have any questions. All right, any questions? Okay. So that's voltage and current. Now, when it comes to voltage and current, again, we're talking about charges being separated between 2 points and current moving from one point to another, right? So we use specific notations to refer to voltages and currents, okay? And the most common one is a 2 subscript notation, okay? 2 subscript notation. So voltage is the difference in electric potential between any 2 points in a circuit, okay? Any 2 points in a circuit. So there must always be a reference point for measurement, right? It's the difference between 2 points. That means you are measuring the voltage at a point with reference to some other point. That's how you determine the difference. So the 2 subscript notation is used to indicate which one is the reference and which one is the measurement point. And if it's VAB, the first subscript is the measurement point, and the second subscript is the reference point. VAB indicates we are measuring voltage at A with my reference at B. Okay, voltage at A, measured at A with my reference at B. And if we flip it and we say VBA, then you're measuring voltage at B with your reference at A. Magnitude would be exactly the same. And we'll talk about signs and polarity in just a bit. But again, two subscript notation. The first one is the point of measurement. The second one is the point of reference. Okay. Now, in the lab, have you all used a multimeter? Or will be about to use a multimeter, hopefully, right? So multimeter has two terminals, right? One positive, one negative, marked as red and black. The black terminal is the most important because that's the common reference point for all measurements. Okay, no matter which multimeter you're using, that black terminal is the most important. It'll be labeled as COM, common. Okay, and that point gets connected to your reference point. So the plus and minus signs that are made here, you can think of it as A is connected to the red terminal or the positive terminal, and B is connected to the common terminal. Again, the reference point is the most important because that's setting our baseline. That's what we are measuring with respect to, right? So if you're measuring resistors, capacitors, voltages, everything is measured with respect to that point. Current is not measured at the same terminal as voltage. For current, you need to physically change the terminals, but the common point still remains the same. The red terminal is switched out, but the common terminal remains the same. Okay. So again, if you are measuring, if the lab asks you, or doesn't matter, you're reading something, it asks you to measure voltage VAB, if you take your multimeter, the positive terminal should go to A, the common terminal, the negative terminal should go to B. If you're measuring VBA, then the positive terminal of the meter should go to B and the negative should go to A. So always keep that in mind. Sometimes some labs will ask you to do that. There are specific procedures to teach students positive and negative voltages. And so that's where you have to pay attention. So VBA, again, plus, minus, red, black. Okay. Is that clear to everyone? Two subscript notation. VBA, sorry. VAB is equal to minus VBA. And VBA is equal to minus VAB. The magnitude does not change. Okay, magnitude, meaning the difference between A and B is not changing. The only thing that is changing is your reference point. Okay, only thing that's changing is your reference point. The reason we put minus sign, is so that we as humans are able to perform calculations and balance out our equations. Okay, voltage in real life is never negative. Current in real life is never negative. Power in real life is never negative. If you have a 10-watt charger, you would say you have a 10-watt charger. You would not say it's a minus 10-watt charger. But electrically speaking, if you're modeling a charger in part of an electric circuit, that's a source, it'll have a minus sign in front of it, right? So in real life, you'll just say it's a 10-watt charger. It's not a minus 10 watt. But if you write a mathematical expression for that charger, it'll be minus 10. In the same way, voltages, currents, they're never negative. They are simply negative from the perspective of the reference point. Is that clear to everyone? One other thing. If the surface of this table is 0 volts, let's say ground, my right hand is point A at 5 volts. My left hand also goes to 5 volts. If this is A and this is B, what is VAB? 0, right? Difference in electric potential doesn't make any difference. It's the same. However, if A goes above B, then there is a difference in potential. Okay. So sometimes ground is used as a reference, then your voltage will only have a single subscript. Okay, your voltage will only have a single subscript. It'll say VA or VB. If it says VA or VB or VC or VD, it simply means you're measuring voltage at that point, A, B, C, D, with your reference at ground, which is 0. Okay, that's again another key term. So if it says VA, VA is measured with respect to ground. VB is also measured with respect to ground, but VAB is measured between A and B. Okay, so single subscript and double subscript notations. That's the difference. And then sometimes, well, actually, I have not seen something like this in a long time. But if you do come across a notation that looks like this, a single-headed arrow, that means plus here and minus here. But as I said, I have not come across something like that in a long time. Typically, voltages would be marked as, sometimes they just marked like this. There's no arrow, nothing. It'll just be like a value here. It'll say 5 volts and a plus and a minus sign, and that's it. So again, it'll be your job as an electrical engineer to understand what it's trying to tell you. Okay, that's double subscript notation. All right, any questions? All right, current direction. Similar to voltage, if you have current IAB, it means current is flowing from A to B. If you're measuring on the meter, positive terminal goes to A and the negative goes to B. Anyone have familiarity with measuring current using a meter? Okay. So you have to break the circuit, insert the meter in the middle, let the current pass through. Oftentimes, if you're in a rush, we neglect the direction of the current, either because we don't know or because we just need to find out. Okay. But if you want a positive value for current, then you look at your circuit, you inspect it, and determine which end is connected to the positive end of the power supply. That's the end where you would connect the red terminal of the meter. And the other terminal would go to the exit point. And again, the same thing. IAB is minus IBA, and IBA is minus IAB. Okay. If it refers to a component, it would just be IR, IC, ID. If it's a single subscript, it's referring to a component. As an example, if you have multiple resistors in a circuit, R1, R2, R3, R4, you might have IR1, IR2, IR3, IR4. Okay. All right. So when we begin circuit analysis, we have no idea of the voltage polarity or the current directions. Since we have no idea, we assign values arbitrarily. We assign polarities and current directions. We assume, we make assumptions. We assume voltage polarities and current directions at random. Okay. But those assumptions are based on certain logic and rules. If we have a voltage source or a current source in a circuit, the polarity of the source is given to us, the direction of the current source is given to us. So we know which direction the current should move. Okay. So we'll make an assumption and then we'll start with our analysis. Now, even if our assumption is opposite of what the actual current might turn out to be, our analysis would not be incorrect. Okay, again, if I assume, let's say we have current I1 in here, right? So I chose I1 to go up. Now I perform my analysis and it turns out I1 has a value of minus 1.5 milliamps. What does that negative sign mean? It's just opposite direction. As long as my analysis is correct, I probably have my magnitude correct. Negative sign is simply indicating that my assumption is is opposite of what the actual current is. As students, for you, if you make an assumption and you end up with a minus sign, you will still get full credit. Okay, you will still get full credit as long as your sign and your arrow direction or voltage polarity matches up. Okay, if the actual answer for this is I1 coming down and you get plus 1.5 milliamps, your answer is correct. If another student chooses to go up and you get minus 1.5, that is also correct. So this is correct, this is correct. But if you choose to go up and your I1 comes out to be 1.5 milliamps or plus, then this is incorrect. Okay. So as students, you keep in mind. So you do not have to redo your entire analysis. If you have a negative answer, I will look at the assumptions that you have made. And if the assumptions and the sign that you have form a complete answer or correct answer, you get full points. Same thing with the voltages. Okay, same thing with the voltages. Any questions about this? Okay. Then let's wait until we are almost out of time anyway. So, all right, I'll just end class here today, and we'll pick up here again on Wednesday. I'll post a reading announcement sometime later tonight. So please check your Canvas websites later tonight for reading assignment. Okay. Did you have a question? I thought somebody had a question. Do you scan it? Did you email it to me? Okay, then I'll just later today or later tomorrow or something, I'll open the submission and then we'll just tally it. So it's the first time. So what's your name? Yeah, got it. So I have it. Yeah, I have it. Yeah. Yeah.
Mastering engineering and everything, right?
Mastering engineering, e-text, and it should last you for
I mean, if
11 and for 12.
the board's
You should not need to have to do it again.
Thank you.
I know Dr. Dolan, I think, is scheduled to teach to 11,
Mhm.
and Dr. Nafisi, he's a very experienced professor, and they both do like to use
That Pearson.
Yeah, Pearson.
Got it. So it should roll over.
And it should roll over and it should work.
Perfect. Thank you. Thank you.
All right, let me wrap up quickly. Hello, how are you?
Good to see you again.
Good to see you too.
How did the class go?
Class went well. Hope